to day 12 of Leetcode 75. This is maximum depth of a binary tree, and this is problem 104. So given the root of a binary tree with return its maximum depth, the binary tree's maximum depth is the number of nodes along the longest path from the root node down to its farthest leaf node. And you could take multiple steps between choosing between the left and the right node that you choose from a given node. So we can say for this example here, example 1, we have 3, 9, 20, 15, and 7. And intuitively, when we're looking at this, the maximum depth we can go is 3. So we can go 3 nodes down from going 3, 20 to 15. And the nulls are just indicating that like 9, like this 9 node here doesn't have any children, while 20 has 2 children here, 15 and 17. It goes by a breadth first search. That's how the root is displayed. So the output is 3, and then for an example 2, we have 1 to 2. So 1 has no left child but has a right child too, and that depth is 2. So the number of nodes in the tree is given in the range of 0 to 10 to the 4, and the value can range between negative 100 to 100. But this isn't necessarily too important for this problem. So the problem that we can, or the solution we can give is essentially just a depth first search, and we can do a recursive solution. This is prone to a stack overflow if the depth of the tree goes beyond a specified amount that Python cannot support. But this can be resolved by using a tail recursive solution where the number of stack frames will become constant, and it won't have to keep reopening the stack frames to populate the compilations from the previous calls, extending all the way down to the lowest leaf node essentially. And the second solution would be an iterative solution where we actually use, instead of using stack frames, we're using a more permanent data structure, such as like a stack that we're using in a list, in which we're keeping count of the maximum depth instead of using those stack frames like we said earlier. So we'll just go ahead and implement the most naive solution that is prone to stack overflow. So essentially, of course, we have to start with our base case whenever we're implementing a recursive approach. So that is, if the root is equal to none, then we can just return 0 since there is no depth if the root is equal to none. Otherwise, we can return 1 plus taking the maximum of when we apply the maximum depth function on the left node and the right node. So why does this solution work? The reason why this solution works is because all we have to do is so when we get to the most bottom part, so say that we get to 15 right now, we're going to be trying to do so say that, for example 1, we've hit 15, we've gone all the way down to 15 by now, and we have no left node, no right node, so we return 0 for those. But now this is 1. We go back up to stack 20, or we go back to node 20, and we've already done max depth on root left, which was 15, so that gave us 1, and also the right root also gave us 1. So we can just maximum of the 2, that's just 1, so we do 1 plus 1. So 20 is 2, return that back up to the third node here, or node 3, node with value 3. And this right hand side, so this root right is 2, so we got 2 depth out of it, while the left hand side 9 only gave us 1, so we take the maximum and we get 2. So essentially it just accumulates between reaching the farthest left or reaching the left or the right. It tries to go as far as possible, and by bringing the values up, we can essentially just keep counting them as we go back, as we keep coming back up until our first root, or until our root node that we reached, and that'll give us the solution 3, and that can be the same with all the other ones. So yeah, that is the solution to this problem.